Hi, welcome to Flight Test Foundations. I'm Jessica Singh Peterson, and I'm going to talk about the importance of flight test. Flight test is one of the things that we do early on in a program before we field a system before it goes operational. And the overall goal is for us to find any of the issues or deficiencies in a system, determine if they need to be fixed, and if so, get them fixed before they're fielded. We always say that we don't want, a new pilot at night over the water downrange to be the one that finds something unexpected. We want to find it in flight test, figure out what's wrong, and get it fixed. I'm going to share with you a real-world scenario that I experienced in my career testing the F-16 automatic ground collision avoidance system. Spoiler, the system doesn't always work as expected, and we actually found something while we were doing flight test. It was opportune because we had the data. We were able to get that data to the prime contractor, Lockheed Martin, who had developed the system, figure out what was wrong, and get it fixed. I'm going to then finish and show you one of the real-world lives that were saved by the F-16 automatic ground collision avoidance system. It saved 13 lives to date, so very rewarding program to work on. And you're going to see in that save, the scenario looks very similar to the flight conditions where we found the issue. So not only did we find the issue in flight test, but also it's relevant to the mission and the need that we have downrange. So with that, I'm going to talk about Auto GCAS and show you the importance of flight test. Thanks. The picture that you see here, this is the F-16, the mighty Viper that I love flying in. It's a supersonic fighter aircraft for the Air Force, and many of our foreign military partners have them as well. You can see the F-16 here flying the low-level route in Southern California. It's about 200 feet above the ground, flying over the Owens Lake bed. The system that I spent most of my career working on is called the Automatic Collision Avoidance Technology Program, ACAT. And there were two major components to this program. The first was the Auto Ground Collision Avoidance System, Auto GCAS. This is a system to prevent collision with mountains, terrain, with the ground. And then the second was the Automatic Air Collision Avoidance System, Auto ACAS, and that is a system designed to prevent midair mishaps. We had multiple features during the duration of testing this program. One of them that I'm very proud of is a feature that was in Aviation Week, where we had a picture shown from our automatic air collision avoidance system testing over Edwards Air Force Base. Now, these systems, we were very passionate about getting them out to the community. Prior to testing these systems, we did a study and we looked at over a 12-year period, so 1992 to 2004, we looked at the U.S. fighter controlled flight in the terrain and midair collisions. And so these are mishaps where nothing was wrong with the aircraft. There's no mechanical failure. It was due to either pilot incapacitation or not having awareness to the situation, maybe focusing on the wrong thing, but many different causes of these mishaps. Over that 12-year period, we lost 86 pilots, 156 aircraft, which is equivalent to about 9 squadrons in the Air Force. It tells you about half of the time the pilots successfully are able to eject from the airplane and survive, which is good. But it equated to $3.7 billion lost. So that's a big number. You can see here, so I have two pictures on this slide that are two folks that are near and dear to the Air Force flight test community. On the left is Dave Cooley. He lost his life in an F-22 due to a controlled flight in the terrain back in 2009. And then the other picture is of Aaron C. George, F-16 pilot, who lost his life in a flight test mission in an F-16. So there's many pilots, and many of us in the community personally know of someone that's lost their life to these unnecessary mishaps that happen. So we are very passionate about these systems and getting them out there to the community. We projected that over a 20-year period, if we were able to get Auto GCAS and Auto ACAS on all of our fighter aircraft, so that's F-16s, F-18s, F-22, and F-35, for the U.S. Air Force, Navy, and Marines alone, we projected to save 172 pilots, 209 aircraft, and $10.7 billion. So really a large benefit if we could get it out there to the mission need. So the driving philosophy of how we design these systems, and I think it's really important because this is applicable not just to automatic collision avoidance, but in my mind, it's applicable to any autonomous or automatic system that's interfacing with a human operator or a human element. The first and the most important is do no harm. So this means that when the computer takes control away and does a dynamic maneuver, it cannot harm the pilot. So it can't be so aggressive that the pilot hits their head and they become further incapacitated, or so aggressive that it structurally damages the airplane. So do no harm. The next is do not interfere. And this is a very important concept for our manned fighter aircraft that have a low-level mission. So they need to be able to fly 200 feet above the ground for terrain masking and being able to stay, under the radar, literally under the radar. So we had to make sure that we did not interfere with that mission. Also for Auto ACAS, the air collision avoidance system, we had to make sure that we didn't interfere with normal formation maneuvering and normal dynamic maneuvering between two or more aircraft. So do no harm, do not interfere. And then the third, which we normally focus on, is to prevent collisions with terrain and other aircraft. What this meant is that by ordering that hierarchy of the systems, we didn't have a solution that would prevent 100% of the collisions that were out there. Now, in testing, we figured that we could prevent about 98% of the mishaps, which is pretty good, but it's not a 100% solution because we had to prioritize the do no harm and do not interfere. And in the next slides, I'll kind of talk to how we tested to that and how the system was designed to allow for that. So I'm going to talk about Auto GCAS, the Auto Ground Collision Avoidance System first. This is the easier of the two because the ground, unless you have earthquake, the ground doesn't move. And so designing a system to prevent collision with the ground is quite simple compared to preventing a collision with another vehicle. It's a system that performs an automatic recovery to avoid the ground when CFIT, which is controlled flight in the terrain, is predicted. It doesn't require any human action. It will maneuver whether the pilot is awake or not. It's the computer taking control away from a pilot and doing the maneuver. I like to pause here and talk. For the Air Force, to my knowledge, this is the first time that we had a computer-based automatic system that was taking control away without human consent or human initialization of the system. Yes, we've had auto land, we had terrain following, many forms of autopilot for a very long time, but all of these systems have been something where the pilot turns the system on and commands the system to do the automated maneuver. So this is the first time in the military setting where a maneuver was taking control away from a human. So it was very important that we got this right. We fielded it back in 2014 on 641 of our aircraft. To date, we've saved 13 pilots' lives, which has really been rewarding. I've heard about every one of them firsthand, or really secondhand, from someone who was a friend of the pilot whose life was saved. And so it's been very successful. I'd also say that the success of this program is what has really opened the door to further autonomous and automatic systems on our aircraft. So because we had that three-piece hierarchy of do no harm, do not interfere, and then do the task, prevent collisions, in my opinion, that is why we've become open to having more autonomous systems within our military. So you can see here kind of the numbers of mishaps, percentages of mishaps. So Auto GCAS will prevent those three pieces of the pie chart on the right. It prevents controlled flight into terrain mishaps, spatial disorientation. That's when a pilot thinks up is down and down is up. It can happen a lot at night or over the water or in the weather. And then also G, loss of consciousness. This is where if you're pulling too many Gs and you're not properly G straining, you can lose consciousness. So designed to prevent almost half of the mishaps that we've had on our fighter aircraft. So I want to talk a little bit about the F-16 low-level mission. So as I mentioned, the system is designed to not get in the way. When I present this in person, especially when I have younger audiences, I like to ask everyone who's seen the movie Top Gun Maverick. I know it's a little bit silly, but I think that movie, even though it's very Hollywood, very much captures the reason that our fourth generation fighter aircraft have a terrain masking mission. They will fly a couple hundred feet off of the ground, and this is so that they can be hidden from enemy radar. So you can imagine that if you don't want to hit the ground, you can just stay high and away from the ground. But for terrain following, you need to be down to a couple hundred feet. And so this is where that balance had to happen. How do we have a system that prevents collision with the mountain or with the terrain while also allowing for flying just a couple hundred feet next to the mountains and turning around mountains? And so that made it very challenging. The other thing that you need to think about is how do you safely test a collision avoidance system without actually causing a collision? And I'll talk about that in the next slides. So our first rule was that to safely test the system, we never relied on the system under test, meaning that if Auto GCAS, if we're flying towards a mountain and we want to make sure the system works properly, if Auto GCAS doesn't activate, we need to make sure that the pilot has time to react and maneuver away from the ground. And so we use something called a terrain clearance buffer, and this is where we'd artificially raise the ground. So we never were truly on an immediate collision course. We always made sure that we had time, and our terrain clearance buffer, the altitude that we would put the buffer in, would change, and it would be a time-based parameter. So based on the state of the airplane, our velocity vector, and how much you could maneuver away, we made sure that we always had at least 4 seconds of available reaction time for the pilot to maneuver if the system didn't work. Spoiler, I'm going to show you a slide a little bit later where the system doesn't work properly, and all of our safety mitigations are what kept the pilot safe for that test point. The second thing is we were doing non-operational diving maneuvers. So these are maneuvers where the pilot had, lost his life, right? And so we were doing things that you wouldn't normally go out and do, flying straight towards the ground at very high speeds. And so we made sure that we always had something we called time safety margin. As I mentioned, this is 4 seconds or more of time for us to recognize a number has been exceeded, to call an abort, and for the pilot to take action and maneuver the airplane away from the ground. If you're diving straight towards the ground, this time safety margin of 4 seconds or more is going to mean that you're going to have an abort at a much higher altitude than if you're coming in at a very shallow condition. We also would monitor the aircraft limits because some of these maneuvers would get very close to the maximum never exceed speed on the airplane because you're diving straight towards the ground. So we had to watch that as well. All of this was more than a single human, than a single pilot could observe while dynamically flying the airplane. And so that's where myself and other flight test engineers come in. We'd either be in the back seat of the F-16, which is pretty fun, watching the parameters, or more often I'd be in the control room watching real-time displays and talking on the radio to make sure that we were doing the test as desired and that we weren't exceeding any of our conditions. Okay, there's a lot of information on this card. You don't need to look at all of it. But this is a typical product that I would create as a flight test engineer. This would come after many, many simulation events and looking at how we were going to do a test point. So I'll talk a little bit about what you're looking from, starting from the top left and down. So this was a smooth terrain Auto GCAS point. So we're diving straight towards smooth terrain below us. We're actually replicating a historical mishap where someone lost their life. So we knew this was a very important condition to make sure that we could save an airplane from. We're starting at a very high altitude. So you can see here 43,000 SALT, which is system altitude. That's the altitude that the aircraft thinks that it is at. The airplane's gonna start level. They're gonna roll upside down, pull the nose low, and we're targeting a fly-up condition where the airplane is almost pointing straight towards the ground, 630 knots, which is 1.67 Mach, so faster than the speed of sound, 85-degree dive angle, so basically directly towards the ground. And we expect Auto GCAS to activate around 33,000 feet. You can see that we have abort limits on the bottom that I'll be watching in the control room. And on the right-hand side, you can see the maneuver schematic. And so this is where we did all of our pre-flight predictions. We predicted that if the system activated as expected at 33,000 feet, the minimum altitude that the airplane would get to during the recovery would be 18,000 feet. If we called an abort, meaning the system didn't activate when expected, then we would get down to an expected altitude of 11,000 feet. And so we had all of these numbers in here to make sure that we had plenty of margin and that would be safe if the system didn't work properly. Spoiler, I'm going to show you a video where it doesn't work properly. But first, let's talk about what you're going to see. So I'm going to show you a heads-up display video, HUD. This is what the pilot is looking through. It's a piece of glass that has information displayed on it. The pilot looks through it in the cockpit. When I'm in the control room, I have a video feed of this information. When I'm in the back seat of the F-16, I also have a video feed, a display that I'm looking at. So it has a lot of critical information that you're looking at. The other side note that I'll talk about is in the control room, much of this data is also sent down, so video from the HUD, but also real-time telemetry display of these parameters. So I have altitude, I have airspeed, I have many more parameters on aircraft state and information on control surface position and pilot inputs. So if we're going to look at starting level, you're going to see the airplane is at wings level, okay, at 44,000 feet and 445 knots. Now, I don't know that everyone here has ever seen a HUD video before, so I'm going to go ahead and describe what to focus on. So there's a lot of information on the HUD. You don't need to look at all of it. The first thing to look at is the flight path marker, which you can see in the top middle. This looks like a little circle with wings and a tail coming up. And so when the flight path marker is above the straight line, that's called above the horizon, you're going away from the ground. When it's below the horizon, you're going towards the ground. On the top left, you can see current G, so that's the number times the force of gravity that you're feeling in the cockpit. The F-16 can go from -3G, which human bodies don't like very much, and hydraulic and oil systems don't like very much. So we don't go there very often, but we can go to -3G, and then can go up to +9G. In this maneuver, you're going to see a little bit of -G as the pilot rolls upside down, then pulls +G, about 6 Gs to get the nose low, and then when Auto GCAS activates, it'll be about a 5.5 G activation. You can see airspeed on the left, calibrated airspeed based on the air pressure that's on the airplane. The maximum airspeed limit on the F-16 is 800 knots, so we're watching that to make sure that we don't get close and exceed structural limits on the airplane. On the right-hand side is altitude. That's based on the pressure altitude measured by the airplane. And on the bottom, you can see radar altimeter, which is height above ground. That is from a sensor that is measuring with a radar the ground below you. You'll note that when the airplane rolls upside down, that sensor doesn't work. And you'll also see that there's a lot of variability. So it's for information, but Auto GCAS does not use a sensor. It does not use radar altimeter. It's just for awareness. It's not very accurate to use for these conditions. Okay, so that's everything that you need to look at on the HUD for these maneuvers. So we're going to start from wings level, and then the pilot's going to start rolling inverted. So here you can see that we're at about a 90-degree bank angle as we're turning, pulling nose low. And at this point, you're going to see Auto GCAS chevrons. So those are the two chevrons that you see coming together, and that means the system is about to activate. Once the system activates, you're going to see a brake X and then the word fly up appear. And so now the computer is in control. The pilot is monitoring what's happening. You can imagine the first time that we did this, the test pilot might have been a little bit nervous, but monitoring the computer, but not adding any inputs and allowing the system to take control and maneuver the airplane away from the ground. Because we're going fast and we're very steep, it's going to take a lot of altitude and a lot of time before we actually are nose high maneuvering away from the ground. Finally, once the system has maneuvered away from the ground, it will say the fly up will go away, the brake X will go away, and the maneuver will be complete. So let's watch a video. This is a test point, testing a mishap recreation. You're going to hear the pilot talking over hot mic to the control room. So he's talking to us as he's doing the maneuver, and you're going to see the system work as expected.
Really good. 450, 1.45. So what is it? Weird.
So rolling upside down.
6 Gs.
Pulling 6 Gs, nose low.
That's good.
Auto GCAS is now in control. Pilot is monitoring the maneuver. but allowing the computer to automatically take control.
Altitude. Control 218, maneuver complete.
So that was a good test point. You can see how much altitude is lost. He started at 43,000 feet and the bottom of the maneuver was down to 18,000 feet. So that's why from a planning perspective, we really have to make sure that we're safely testing and simulating these events before we go out and fly them. So as I mentioned, one of the big things as a flight test engineer that I've done in my career is creating these test cards. I described many of these different things that are on here. We put in a terrain clearance buffer of 6,600 feet to artificially raise the ground. We have a fly-up condition that the pilot is trying to get the airplane on. He's very focused on getting on condition. In the control room, I'm watching abort parameters to make sure we don't get too low before the system activates and that we don't get too fast. I'm going to make sure we don't exceed the aircraft limit. Okay, so now let's talk about the comm plan, the communication plan. I'm going to show you this because we're going to watch a test point where the system doesn't work as expected and we have to use this communication plan. So it's critical during tests to be able to communicate quickly and clearly. Words have meaning. So when we say abort, 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 it's urgent and action needs to be taken. We would use this if there was a system malfunction, so if something doesn't work properly, or if we would breach a planned altitude. The pilot would have a specific recovery procedure. So he's going to roll wings level, pull the throttle to idle, and put out the speed brakes, which adds drag so that you don't get too fast. Again, remember, we don't want to exceed that 800 knot limit on the airplane. And then he's going to pull to 6 Gs to maneuver away from the ground. So let's see how the comm plan is applied. So here's why we do flight tests. The system doesn't always work as planned. You're going to see this test point looks very similar. In fact, it's the exact same test point to the one I just previously showed you. However, the system's going to fail. You see on the top left of the heads-up display the word no GCAS. And I call this the blue screen of death. It's where the system did not have enough processing power and it wasn't able to process everything it needed. It failed and Auto GCAS was no longer there. What you're going to notice is that the pilot doesn't even realize the system has failed. The control room calls an abort. The pilot manually maneuvers away from the ground. And while he's in the maneuver, you'll hear him say the words no GCAS as he realizes the system has failed.
630 by 34. Zoom on commence maneuver.
So same test point, same pilot, different day.
6 Gs.
Pulling 6 Gs to nose low.
Release.
Release, he's waiting. You see the words no GCAS.
And idle, full, board.
That was a control room that called abort.
No GCAS.
You can see that he realized in that recover no GCAS. So that's why we do tests. The good news story is that while this never happened in the simulation, and it only happened about half the time that we were doing a flight test, we found it, we collected the data, and the contractor, Lockheed Martin, who had created this system, was able to take that data, determine what was causing the issue, get it fixed, and now we have a fielded system that no longer has this problem. So this is why we do flight tests, and it's why we do all of our safety planning. So I'm going to leave you on the Auto GCAS side with this. And this is a real world save. If you go on YouTube, you can find this video. It's been publicly released, just like everything I'm showing you today. But this was the 3rd or maybe 4th save that we had. System had been fielded. This is a new pilot in the F-16. He has a bad day. He pulls, 8 Gs, 9 Gs, loses consciousness in the airplane, and his aircraft starts barreling towards the ground, faster and faster. You're going to hear over the radio his wingman, so another F-16 pilot in a different airplane, watching the aircraft barrel towards the ground, expecting to see a fireball. You're going to hear him saying over the radio, 2, recover, 2, recover, trying to wake him up. Fortunately, Auto GCAS comes on, saves the pilot's life. He met us later and told us that he woke up in the airplane and thought he heard his alarm going off in his bed. Was able to recover and come back and continue training and become a qualified F-16 pilot. So let's go ahead and watch this video. The last thing I want you to take away as you're watching it is how similar this maneuver looks to the scenario I showed you where we had problems and we found them and fixed them. So it's important to find these issues and fix them in test before we put the systems out with humans actually relying on them. So the pilot is turning and pulling. You're going to see him pulling G's. Look at 6 G's, 7 G's, 8 G's, and now he's passed out. He's getting more nose low and faster.
Fuel recover.
That's his wingman.
Fuel recover. Fuel recover. Fuel recover.
Auto GCAS is now in control, maneuvering away from the ground. The pilot is now awake. You can feel him breathing pretty hard.
Gully, knock it off. Gully 1, knock it off.
Gully 2, knock it off.
You get yourself back above the floor.
So this is why we do tests. And I'd tell you, very rewarding. Probably one of the highlights of my career was when this pilot came and met us and thanked us and knowing that he was alive today because of the system that we fielded. So very important. Okay, I want to talk a little bit about the automatic air collision avoidance system. Now, this has not been fielded yet, and this is a much harder problem. So getting the system out, you can see this is a picture that we took over Edwards Air Force Base as we were testing the system. How do we prevent mid-airs between 2 or more aircraft? Same philosophy, do no harm, do not interfere, and then prevent collisions. You can see the numbers here. Here are the historical mishaps on fighter aircraft. And auto ACAS, about 25% of the mishaps that we have would be preventable if we get auto ACAS out there. So how does the system work? As I mentioned, it's not fielded yet. It's very challenging. We implemented this on something called an Air Combat Maneuvering Instrumentation Pod, an ACMI pod. It has aircraft state information and it has a data link. I think it's at about 20 hertz that it's sending information out to other aircraft and receiving information in from other aircraft. So I'd call this cooperative. There are other, I don't have time to talk about it in this presentation, but we also looked at non-cooperative where you'd have sensor information. So what does this look like? As you're flying towards another aircraft, it's transmitting information. The other aircraft is receiving that information. It's considering different types of maneuvers. And then at the last moment, it will activate to maneuver away from the airplane. This is obviously simulation video that I'm showing you. What does it look like in the cockpit? So from the simulation, again, this is what the heads-up display looks like. You can see chevrons coming in, and then at the last second, it's going to do a 90 right to avoid. So that's kind of a high-level description of how the system works. So the big thing that we had to deal with is how do you test a collision avoidance system without actually causing a midair? This is where we had to balance being effective. So we wanted to effectively test the system while still being safe. We had new test techniques that we were looking at. It required innovative safety planning, and we had competing objectives to be effective and safe. The more safety restrictions that we took, the less like a midair mishap that it is. And then the more it's like a real midair mishap, the more likely it could become a real midair mishap. So the first thing that we did, and many of you might be thinking this, is we used a virtual partner. And so we did a safety buildup where we had a virtual partner that was being transmitted into the air, and then we were doing maneuvering across it. I will say the big challenge with this is winds aloft. The real airplane is flying in real air mass with winds that I've seen as much as 100 knots when you're up in the air, and the virtual airplane is not feeling that. Even if you try to type that in, winds aloft change very quickly in geographical areas with mountains and terrain. And so that made it very challenging to create a virtual midair mishap. So we did this a little bit, but it ended up not being as efficient or as effective as we had hoped. So we had to start thinking about how do we do this with real airplanes, 1v1. Well, similar to Auto GCAS, we had the rule, do not trust the system. And so we would put in exclusion zones that were interlocks so the flight control computer could never command a maneuver towards the other airplane. It prevented a roll and pull, and the algorithm was unaware. So the algorithm could request a maneuver, but the flight control computer would not abide by it. So that kept us safe. We also had a bunt inhibit that would prevent the airplane from bunting. We had to think about this for every single geometry that we were going to test. The next, similar to Auto GCAS, we never relied on the system. So we wanted to test this without actually being on a collision course. The way that we did it is we had an altitude split. This is the actual distance, metal to metal. Okay, so if one aircraft is at 20,000 feet, well, 20,000 feet, we'll say the bottom's at 20,000, then the top will be at 20,000, maybe 200. And so that would be our altitude split. We would then fool the computer to think that they were basically co-altitude. And we put a little bit of an offset so that we'd have a little, what we call a consistency kick. So let's say we had a 200-foot altitude split, then maybe we'd have a 180-foot altitude offset. So they're almost co-altitude, but not quite. And that gave us consistency in the types of maneuvers the algorithm would select. It was pilot selected and had to be typed in. So I'm going to show you next the test card, and you have to think about how important all those different settings are. So this is what our test card looks at. Lots of stuff. You don't have to look at all the numbers, all right? But I want you to take away that these settings that had to be put in to be able to safely and effectively test the system. So altitude offset here was 150 feet. I didn't quite remember the numbers. And then altitude split, this is where we had a 200-foot altitude split. And then finally, the exclusion zones. So the aircraft that was down and to the right can't go up, and the aircraft that is up and to the left can't go down. And so that's how we made sure that we were safe. Now, we did many of these test points. I'm only going to show you one. This is going to be where we have a shooter aircraft down and to the left, target aircraft high and to the right. The first video I'm going to show you is going to be this video on the bottom left, and it's from the target aircraft perspective. You're going to see the airplanes turn in towards each other, and then the computer is going to take control and maneuver them away. So high and to the right is turning in. System thinks they're co-altitude, and then automatic maneuver. And then good flight test engineer putting his head down and writing notes. All right, the next video I'm going to show you, and warning, sometimes these make people feel a little queasy because there's a lot of movement going around. This is from the pilot's perspective. So he's wearing a pair of glasses that have a little camera right here, and you're going to see what he's looking at. I want you to notice that he's spending most of his time, he looks at the heads-up display, but most of his time looking at the other airplane, the real metal. And so this is why it's so important to have either a backseat flight test engineer or someone in the control room monitoring the parameters, because the pilot is not able to look at everything. They have to focus on the dynamic environment that they're in. Again, looking at the heads-up display and then looking up and right to the other airplane. And as they get closer, you're going to focus mainly on the other airplane. So as I mentioned, the system is still in development. I've heard rumors that we're going to get it out there very soon, but it's very challenging. Lots of considerations that I don't have time to talk all the way through to make this system work on our fighter aircraft that fly very often in very close formation. Having that balance is very challenging.